Go ahead and get started. Welcome back. This is, I think, a pretty critical topic for us to cover. I didn't say exciting topic, I said critical topic, so let's do our best with it. And just definitely let me know as we go through this as you have questions. Ultimately, I think when covering a new type of way of handshaking or a bus interface, there's probably no shortcut for understanding and reading through the documentation and getting a feel for it yourself and seeing it in the tools. But short of doing that, here's my attempt to try to cover it at a reasonable enough level of depth so that when you do dive into the documentation and use the tools related to this, you don't feel completely hopelessly lost. You at least have some intuition for what I am talking about here. And just remember where we were last week. We were talking about different ways of interfacing between two components. You have a sender who wants to send something and a receiver who wants to receive something. And part of what we walked through last Thursday was it's not always as straightforward as it seems. If we have components that are operating completely synchronously with each other, then you just have interface signals and you're done. But there's all sorts of complexities typically. We have a state machine running in the sender, we have a state machine, separate one running in the receiver. They could in fact be operating at different clock frequencies. And if we're not careful with how we do that handshaking, we can lose data. We can actually get data received multiple times when it was meant to be received just once, or we can just miss data entirely. And we walked through the various types of handshaking signals, and the one that seemed reasonably good for resolving some of those miscommunication issues was the four-way handshake, where we have both kind of a request and an acknowledgement signal, request coming from the sender, acknowledgement coming from the receiver side, and we would both wait for them to go high for the start of the request and also wait for them to go back down, essentially as an acknowledgement that the request has been received. We also talked on Thursday about FIFO interfaces, how they don't entirely solve this issue of communicating between a sender and a receiver, but they provide you that buffer. They use as a trade-off an amount of memory to kind of store intermediate sent values so that assuming you take some care to monitor whether or not the FIFO buffer is either full or empty, you can also resolve those handshaking and those communication challenges. This topic is we're going to talk about the advanced extensible interface, or just the AXI bus interface, is directly related but not meant to be a replacement for the concept we were talking about last week. This is an example of a specific standard for communicating in embedded systems, and we can look at their solution to the handshaking problem. This solution matters because we want to build systems that are fluent in this bus protocol, and so we have to be aware at a much more lower level of detail what is happening with regards to the signaling here. So AXI, the term you may see otherwise in other places is AMBA for ARM Advanced Microcontroller Bus Architecture. They're referring to similar things, is the kind of de facto standard for ARM-based embedded systems. So in almost any kind of embedded product, your cell phone, anything that uses an ARM processor in it. There's actually a fifth version of the AXI standard, but looking at devices still released today, they either have their own kind of bespoke version of it, or they're still on AXI 4 by and large. There are three main variants that we have to understand, not just as kind of a conceptual in-class thing to learn, but because the system that you are building for MP1 and beyond is using all three of these. You'll hear different terminology for that as well. If you just see the term AXI 4 describing the bus interface, that's referring to the full AXI 4. The other term you'll see is kind of the memory-mapped AXI interface, and we'll talk about why it's called that. There's also the lighter version, or AXI 4 or AXI 4 Lite. That's just a subset of the more full standard, and it's useful for certain things where you don't need the full standard. And then separately, there's the AXI Stream standard, which shares the same name, but doesn't actually do something similar. It's more of a FIFO-type interface for AXI system. They all are going to involve some level of handshaking, but they're going to be used in different scenarios. By and large, this semester, I tell you which one to use and why. So by and large, you don't have to make that decision as a group as you're working on things, but you are still writing code that's interfacing with either AXI Full, AXI Lite, or AXI Streaming, and so you have to be aware of the signaling and how one does interface with that. Ultimately, you still have to read the data sheets. That doesn't go away. Or look at waveforms. You can do it either way. Either try to understand what the waveforms are doing or try to understand the data sheets and then look at the waveforms. But this is my high-level overview, and we'll try to do a little bit of hands-on exercises with that today. And I hope then going into the lab tomorrow as a team, you feel a little bit more confident finishing up that part of the MP1 assignments. So this is one view of the AXI full kind of interface. There are 5 different channels. That's the first thing you'll read about when you read about AXI 4. Channel's just a more complicated sounding word for just a set of signals, set of wires, set of interface ports associated with a part of a transaction. So there are 5 different channels, which is different than how other buses would potentially do it for different parts of both the read and the write operation we may want to have. AXI and AMBA still use the terms master and slave. We can try to use sender and receiver, although you'll have to do that mapping in your head when looking at the documentation. For a read transaction, there are 2 channels and 2 different stages of a read transaction. There is first, when we say the word transaction, you can also think of that handshaking, right? There's an initial handshake to get an address and some other read-related operation data sent across. That's the first step. Then there's a separate handshaking for that data to come back off the other way. When there's a write request, there's 3 channels, which is also not always the case in other standards you may look at. There's an address phase, and a channel associated with that. There is a write data phase, and you see the arrows indicating which way the write is happening here. And then in AXI, there's also a write response stage where you have to get some confirmation from the receiving side that the write actually happened, and you have to wait for that before you can do the next write that you may want to have. That is a lot of overhead, even just conceptually, in terms of what has to happen for either a single read request or a single write request. There are either 2 or 3 sets of handshakes that happen for that. And so it does seem like that'd be a lot of overhead if I just want to transfer a single byte over, and that would be the case. What all these kind of high-performance bus standards also allow for is the so-called single address, multiple data mode of operation, or just burst mode of operation, where it is still a single kind of pair of handshakes between address and data for either read or for write, but we can specify that as part of that address handshake, we're going to be copying more than 1 block of data over at a time. So there is still that overhead. We still have to agree upon the read request that's being requested by the sender. We have to agree on the address. We have to get that signaling done. But then the amount of things we can read or the amount of things we can write in the write channels that we have here can be more than just a single value at a time. So there's still the overhead, but it's somewhat amortized by that. You do the initial setup, and then you have multiple beats of data being sent over that either data read or write data ports. So this should look kind of similar, just straight from the AXI data sheets for that handshaking. So for every one of those channels, there is that valid/ready handshake going on. I think we call that command and ACK or request and ACK on Thursday, but it's the same concept here. The sender is going to be specifying a valid signal, and that's what valid means in ACK. It means ready to send something, either address or the actual data I want to send. And it has to wait for a ready signal from the receiving side. That is my ACK type of signal or my ready for send type of signal here. And each of those of the 5 channels is going to have a combination of those. So there's going to be a valid ready for the read address channel, a valid ready for the read data channel, and a valid ready for the 3 write related channels as well. As you start to build a state machine to potentially be on one side or the other of this type of transaction, you have to be aware of the somewhat flexible signaling functionality here. The whole point of having a ready signal, as that diagram in the upper right here shows, is the receiver side doesn't have to be ready at all times. It can choose when it's at the right point in its own state machine to be ready. That concept is called inserting a wait state, which is to say, I'm ready when I'm ready. The sending side has to wait until that ready signal goes high. But you can also have other devices that are always ready, which is to say, they can always receive data and you can check that signal and it's always going to be high here. And then finally, there are some receiver side modules that will have the so-called same cycle acknowledge that it's actually monitoring the valid signal and it sends its own ready signal high as soon as it sees that the valid signal has gone high. The only downside of not doing that correctly is maybe you're losing a cycle or 2 in doing that handshaking, but all 3 of those possibilities are there. So 5 different channels, each of which has its pair of handshaking signals, plus all the signals we need to have to be able to do things like send up to 256 data beats in a single read request. The first thing you will notice then when you actually look at AXI in practice is really that disconnect between the kind of concept and then the actual practice of doing it in a real system. I think the first thing you'll notice, this is my attempt to show just some of it, this is just for the read side, there's just a lot of signals to keep track of. And there's no avoiding that. I guess that if you have something that's going to be compliant with this bus interface, you have to have this set of signals associated with it. It turns out for a number of these signals that listed here, there's some defaults that you can just keep those wires at and the system will work reasonably well for you. But at the very least, you have to be aware of address length, address, comma, length, comma, size, comma, and burst at the very least here. Things like whether you're locking an interface or there's some caching or some other information going on here, you probably can keep it some sane defaults, but you're going to provide an address, a burst length, and the size of that burst. So length is how many beats in the burst, between 1 and 256 things that we are going to send. Burst size is how big is the amount of data we're sending in each burst. And then there's different burst types in terms of how are we incrementing the address as we do that burst operation here. That is for the address channel itself. So we provide the address / control information. There's a handshake that happens here. That's why there's address valid, address ready signals. All of these signals here are output signals from the master's perspective, from the sender module's perspective here, except for then that ready signal. That's coming from the receiver side. That's the one that we're monitoring to see if the receiver side is actually ready to receive that data. If it helps, it may or may not help. All of those signals are starting with that prefix of AR. That's address read or AXI read prefix for all of those signals here. And then we have then the actual read channel for which we're going to, at the very least, get some sort of response signal that's valid or invalid, and then the actual data is going to come back out over that port as well. And your timing diagrams, both in data sheets as well as in practice, tend to look messy. They're not super clean like the kind of conceptual examples we did last week here. So in the read request, what is going to happen? We're going to have some other logic that's not shown here, right? There's the actual logic in our IP core that's doing some viewport calculation or something like that, right? It has to determine at some point that, yes, I am now ready to do a read request on an AXI bus. That's never shown here. That's always separate logic that then is going to connect to this logic that you would have to create to interface with the AXI bus. But you have to assume that to start a transaction, there's a valid desire to read some data from some location somewhere in your memory. So that's a given, but someone does have to generate that logic at some point. As part of that, it needs to know that kind of, like whatever you want to call it, control information. You can call it metadata associated with the read request. We need to know what address do I want to read from, and that could be a 32 or it could be a 64-bit address in your memory map. You then also need to know how much data do I want to read. Is it a single 32-bit value, or is it 256 64-bit values? You would then set the other control signals accordingly. This one doesn't show the burst, but there's two stages associated with that transaction. There's first the handshake of the AR valid, AR ready signals. So as the sender or the initiator, I set AR valid high. I know I'm good to go once I check and see that AR ready has also gone high. This shows AR ready going high. Let's see, this clock cycle, this is the rising edge of the clock in our design. AR valid, the receiver has checked that it's gone high, does some sort of if statement, some sort of latency. It then says it's AR ready high. At the next rising edge of the clock cycle, my interface detects that AR valid is high. I now know I've transmitted that address information. There's no guarantee it happens right away. This doesn't show it happening, but from AR valid going high to AR ready going high, I don't actually know if there's even a limit. It could be an arbitrary amount of time that your side has to wait for that to happen. That's why state machine makes sense for that kind of implementation. You're in the address send state inside your logic. You set your address to what you need to be and the other control signals. You set AR valid to be high, and you wait until you receive that AR ready signal done. At that point, there's an arbitrary amount of time until you have decided now that the address has been latched, that information has been sent over the bus. I now should be expecting at some point to be getting some data back. This is the only part that can be a little bit tricky here. These two signals are from the sender's perspective. These two signals are from the receiver's perspective. It's only in read requests where who is doing what is kind of reversed, right? The sender sends the address, but it's the receiver who sends the data back, right? So that's the only time that this is a little bit reversed in terms of who is doing what here. I am specifying that I am ready to receive that data. I would think for most systems that you yourself would be building, as soon as I know I've latched the address, this is showing an extra wait cycle just to show that such a thing is possible. I would assume that you'd be ready to receive data in the next, presumably in the next cycle. I've sent the address. I'm expecting data to come back. As we have systems that are cores connected to cores connected to cores, it could be waiting for something else to be ready for this core itself to be ready. So you can't guarantee it's always ready right away. I am specifying as what was initially the sender that I am ready. I know that I have valid data once I see that valid data signal go high from the receiver side. That indicates a single beat of a burst transaction happening. They both sides should then have an understanding, depending on the signal that's not shown here, our AR length information, that I'm expecting between 1 and 256 beats of a transaction happening here. And in this case, there's 4, that's all it's showing here. They're both going to wait until we both have those signals high, 1, 2, 3, 4 times. That indicates those 4 transfers have happened and our read transaction has finally occurred. Yeah, sure.
So on here, you've got AR length for the burst length. What's the difference between that and burst size?
Yeah, that's and then there's also AR burst for burst type. Burst type, I have to look at the documentation. There's different bursts where, for reasons that aren't immediately obvious unless you're working with like DMA type systems and interfacing to FIFOs, sometimes you want to burst and you want to send to the same address multiple times. That UART from MP0 is not a terrible example. I want to send 256 bytes to that UART, but the UART only accepts a single address, so I'm just bursting to the same address. Usually, I think if we're thinking about reading a block of data from a memory, you want to increment the address each time. That's AR burst. AR length is the number of beats in a burst. So in AXI4, that's 1 is the smallest value, 256 is the largest. You have to do a little bit of math because the value of 0 encoded as length actually means 1. You never want to send it as 0. And then AR size is the amount of bytes that are being sent in every beat of the burst. There's reasons we sometimes have to do this, right? It's not actually shown here, but our data can be of different sizes, bit width. So it could be 8, 32, 64 bits. That's on the sender side. The receiver may not be capable of sending that much data at a time, and so we may have a need that the sender side is capable of handling 64 bits of data. Maybe the receiver is only going to be able to send 8 bits of data at a time. You would set AR size accordingly. That's a valid question. It's a good question. There's a bunch of different places you can read and really get to know this in practice. I think, unless it's your goal in life to become a master of AMBA bus, AXI bus, what's most relevant to you, I think, is, what does this mean for my design for the simple graphics processor in lab? There's a lot still to cover just to answer that particular question, but for me at least, looking at software specification helps or can be more helpful than looking at just data sheets. So some of you may have already looked at this code before. This is the include file for the simple graphics processor driver that at least in part is provided for you as part of MP1. Hopefully one member of your team is the driver person, or collectively you're all driver people. Part of this is to determine how do we actually send data from the workstation running OpenGL application to your hardware in which we are doing the actual processing of those commands that are coming. And this one is low level enough that you never need to change this for your code. But if you really want to understand the data that's coming over the line and what values for the AXI signals we're sending, this was my attempt to encode that directly in the driver itself. let me back up a little bit before I go into too much detail of this. This is the high-level view of the simple graphics processor. Yeah, things get added to it between MP 1, 2, 3, and 4, but this high-level diagram doesn't change. That's not readable. I'll describe what I'm seeing here. There's so-called system interconnect, that's critical. There's the graphics subsystem where all of your logic is effectively going. And then somewhere on here, there it is, there's the so-called Ethernet subsystem here. That is the module by which we are getting data on and off the board. I'm going to quickly talk about what's happening here, but this will be quick because it would take us a decent amount of time to really be true experts on what's happening here. This module should be here somewhere, has a so-called UDP over Ethernet design. UDP is a different design choice than like TCP, but this is processing IP packets, effectively what this is doing. So it's doing all of the low-level Ethernet signaling for you. You don't have to worry about that. It's got a physical set of pins corresponding to RGMII Ethernet mode here. It's receiving Ethernet packets. That's what you can think of that from here. This is receiving Ethernet packets. We need to actually send data off this to get to the rest of the system. We have to do some complicated handshaking. Well, we got a FIFO there. It's labeled really detailed so I can keep track of it, but that's an AXI4 stream, which we will talk about today, still FIFO here. Next to that, there's some tagging of data that was needed to get this next module to work correctly. And then there's this unit. This is the AXI memory map to stream mapper. You will eventually get pretty good at reading these signal names and recognizing what's there or is not there. AXI means AXI bus, obviously. Memory map was just another term for like AXI full, so like full signaling that we're learning here. To stream, this is getting converted to an AXI set of stream signals, and it actually works in both directions here. This takes a set of Ethernet packets, or UDP over IP packets, sent on the Ethernet bus here. A little bit of FIFOing, a little bit of extra data getting added to it. And it is generating a set of signals that is M_AXI, and it's just labeled. That is a master, our sender, on the AXI4 memory mapped bus. This module, which is unfortunately very poorly documented by Xilinx, is the one, and if you ever look at their Xilinx forums, the only answer you'll get is, don't use this module, you should never be using this module, but it does exactly what we need for this design. This is the module that takes the Ethernet packets, generates AXI signals from it. It is doing a lot of the heavy lifting. I actually have the data sheet open here, because it is a non-terrible description of the AXI interface. It's basically serializing all of those AXI signals here. That output, we have to kind of follow along in our design to see where it goes. We will see it eventually. It's over here. That's connecting as a sort of a sender port on this interconnection. Ultimately, it's going into a switch, which we will also talk about, and then potentially connecting to the whole rest of the design. So that's you can think of that as a bus switch or like a router. It's saying from that Ethernet core that's there, generate the correct set of AXI signals and then send it off to the rest of your design. That is what our driver then has to interface with. Given the documentation about how we order the actual bytes of the AXI signals, you can then look at this file and see exactly what values for these AXI signals for the read and the write transactions we are providing here. And it has to be kind of bit accurate to actually work with that core. We really can't necessarily fake it here, but you can start to see what actually is going into that individual. I label it as A_X here, because the data sheet does, because this could be both for the read and for the write side. So it's both read and write signals. They're the same for the address mode. And here we're specifying there's 2 bits for the burst type. There's 3 bits for the size. Somewhere there should be length. And the length is kind of annoying. It's 8 bits for the length, but it's split across 2 different packets, so we have to split it across 2 different packets ourselves. And then some of that other information that I said wasn't as critical there. Then when we actually want to generate let's do a read request because that's what we're talking about right now. We have some data that we're interested in sending, and we then just set in that structure those signals corresponding to, going to your question, AR burst, AR size, and AR length. For burst, we always do AR burst increment mode, which would be defined in here, but the actual bit field for it doesn't necessarily matter. We're always sending in this system a 32-bit value per beat of our burst that's for AR size. Where's our, 1 second, that was the wrong one. Where's AR size? Thank you. 4 bytes, that's that value, that's just hard-coded there. For the type of burst, we're always doing the incremental burst, and those are the 3 burst types that keep the address fixed if you're interfacing with a FIFO. Increment the address, or does some sort of wrapping thing if you know that it's aligned on a 16 or 32-bit byte boundary. We're going to be sending it via a burst request, and then we generate the amount of beats in our burst via some unfortunately complicated logic to get a 8-bit value back out to determine what the actual burst length needs to be. This function takes the burst length as an input. 1 is just for a single beat, 256 is for the maximum. We then encode it by subtracting 1 from it, so that's 0 for a burst length of length 1 and 255 for a burst length of that. And then we actually generate that packet, and then later on there's a function that actually then does like the UDP networking to actually send it over the bus. That packet goes to the Ethernet core, then it connects to this memory map to stream or stream to memory map pair that then actually does all that signaling for us. Given the data of, okay, this is a request for 16-beat burst starting at this address. That was the packets of data that was sent over my FIFO interface to this component. I am now going to do all the tiling of those signals high and low so that you don't have to for your IP cores. And because it's all just going to ultimately be a memory mapped system, we specify in our driver, I want to send 32 bytes to location 10,000 hex in our system. Ethernet core grabs those bytes at a time, connects them, tags them so that they're appropriate for this really weird model that we're interfacing with this. This then allows us to then, via the Ethernet request, send data anywhere we want in our system. That was the read interface. The write interface is just more because there's that third channel here. So there's just 3 steps being shown here with our non-posted write module. Handshaking for address, handshaking for every byte of the data that was sent over the channel, and then at least a final handshake for our write response that yes, everything went correct, everything went okay. The logic for interfacing with a bus like this can get very complicated. For our logic that we write, we generally assume we're going to get an okay signal back out. It's not really that clear to me. What do we do when we get that something was not okay? Do we just try the whole thing over again? It's not clear, so we assume there's okay, and if there's not okay, well, you set a signal somewhere. You set a register or something to say that something went wrong with the transaction. It generally works pretty well for our purposes. I want you to give it a try. Let's take about 5 minutes. Chat with someone near you, scooch over if need be, and let us try, knowing that it's not going to be perfect because we're just doing this via pencil and paper right now. But they try to design an FSM that when you've triggered it, writes a burst of 8 values over an AXI interface. Just do the state machine and don't worry about the VHDL for this for now. As I said, draw out the state machine and the VHDL or Verilog you will figure out reasonably soon, right afterwards. So an 8-byte or an 8-value burst, I didn't even specify the size of the data, so an 8-beat burst of data. There are going to be more than 2 states for this because we have to do the address latching phase, and then we have to do some sort of counting of data value phases, and then this is a write request, so there's that final phase at the end to get our write response back out. Take a few minutes, don't do it by yourself, sit next to somebody, give it a try. I'm just curious what you're able to come up with if anything, for this.
Yes. Yeah.
Just leave those. We'll give this a try.
You set valid when you set the index, and then you set setting values. I mean, when you set the
Oh, I see. Yeah.
Take another couple of minutes on this. We'll see what we can come up with.
sure. Yes.
This doesn't have a last field. We'll talk about last field as when we talk about axis string.
So W valid.
Oh, yes, there's last. Okay, W valid.
Should we account for W last?
It's not clear. I mean, yeah, I guess it's here. Let's not worry about it. Both sides should know when it's the last anyway.
Yeah.
Last can also mean different things. It could be something more. Application is not the right word, but it could be one layer higher in type in terms of our interface here, where last means this is the last vertex in a triangle, or it's the last triangle in the scene, or something like that. Because both sides should be aware of how many valid transactions have happened here, with valid high and ready high. Whether you include that or not, we should be able to get it to work. All right, let me see if I can get the technology here to work for our purposes. We'll have to swap back and forth a little bit, but we'll give it a go. Okay, let's give this a try. At least it's not upside down. Okay, we will give this a try, and no guarantee of it actually working here. I would say that's not going to work very well. All right, well, some of you, talk to me about what you've implemented here, or what was your concept? So we know we have at the very beginning That almost looks invisible. I could try the marker here. That's not going to look good, but we can try it here, and then we can all make fun of my lack of handwriting by the time we're done. That at least should be visible here. I'll try to get it to work, but we may have to kind of simplify it a little bit. That there has to be some sort of wait for start. Wish me luck here, folks. Wait for start, where it's just kind of spinning and waiting on that start signal. That's whatever other logic your IP core has. So we don't even know or care what that is. That depends on what am I wanting to send in the first place. So you could also think of that state as all your other logic in the core that's doing what the core needs to do. And if that's a signal that it's set at 0, now we got the start signal saying, hey, we're actually going to start to send. And we know there's going to be 3 steps of our send. Now, I do like to separate, the concept of what we're doing in a state machine from the implementation, but just a small word of advice that, the 2 process state machines tend to work pretty well in terms of how to implement these things and get the results that you generally expect. That would be one process that's reacted to the clock, that's a synchronous process that checks current state as well as inputs and determines when we should be to the next state. And that would be a process that's just doing that. I'm going from state A to state B to state C. That's a nice thing to separate out because you can really reason about it just looking at the code. And your diagram should match the code pretty much on a 1-to-1 correlation there, right? That rising edge of clock, I have a register holding the state information, then I go from this state to that state to this state based on some combination of input signals that we have here. And then you would have a second process. That second process I typically do as a purely combinational process with no clock at all. So you have to watch out for sensitivity lists and the like. That process would be sensitive to the current state as well as to the inputs. And that would determine what my output should be based on the state that I am currently in. That allows me to write my state machines, and I'm literally running out of space already here, but to be able to say things like, I'm at this state called send AW address, and I know what I need to do, right? I need to actually send that signal or set that signal. I'll come back to this in a second. Is equal to, it was called in this spec here, input address. Let's see if this is readable at all. No. Now it's really better. Trying to record it here, folks. Technology. There we go. Okay. I'll just have to move it around a little bit. That's setting my AW address to the input address. For me, at least, I would just have that be, you don't even need a state machine, you don't even need a process if this is just one line of kind of data flow logic. When state is send AW address, set AW address to input address. Or you put it in a process, but it wouldn't need to be a clock process. When we're in that state, I'm sending that address. What also should I be sending when I'm in this state? The valid signal. I am sending that, yes, we are both in a state of sending the address, and I'm also sending that valid signal. I didn't show it for the other transition, but when do I transition away from this state? I'm in send AW address. When do I transition away? Yep. Now, we could also draw it as like a little feedback loop where when AW ready is 0. This also, I think, is probably sufficient to indicate that that's happening. I'm sure you appreciate the extreme zoom in on my hand there. That when AW ready is 1, I can transition away from this state. Because that implies that the valid was high, the address was latched, and the receiving side is actually ready. What should I call the next state that I transition to? Again, the temptation is just to call it S0, S1, S2, S3. Just I understand that temptation, but try to call it something that you can go back to and kind of try to remember what's going on later on. What should we call the next state? Somebody else. No pressure, Ben. Thank you. And if we want to really use our AXI kind of terminology, I would probably just call it send, write data. Ugh. You're never sending read data from an AXI sender or initiator, but send W data is happening in that next stage. What do we need to do for send data? Yep, and that would be W valid. We're sending W data. When we get that ready signal back out, now if this is a burst transaction, we probably can do so without adding a wait state here, and that's perfectly valid if you were to do this. But when we get that, we got that ready back out, which is our now W ready signal. You can't see what I'm writing. When we get that ready signal back out, that the data has actually been read, I would probably do something like, just to get it to work, and then I worry about trying to overlap my updating and my sending of data. I'm sending 8 values here. I would call this state like, update W data or something like that, which is technically going to cause us an extra cycle of latency for every beat in our 8-beat burst here. It's going to work, and then we can worry about kind of trying to do that all in one complicated state. Because there are other things that is not shown in this diagram that we also have to kind of specify as being necessary here, right? When we are in the send AW address state, also send all the AW, we'll call them XYZ for want of a better word, all the other signals that we need to send it at that point here. That's a little bit better. Actually, that's a lot better. Things like the burst and the length and the size and the protection and the cache. Basically, I think if you're in doubt, you can look at kind of like the defaults that we're doing here and the bit encodings for that, and that actually gets you pretty far. All those other things we're sending at this point. So for example, for AW length, this example, we are sending an 8-byte burst, I think is what I said here, an 8-beat burst here, burst of 8 values. We would want to set that value to 7 for reasons we just talked about with regards to there's kind of an inherent +1 happening behind the scenes here. We then send AW address, we send AW data. Somewhere here we are, update counter. So you have some other logic which would probably be, personally I would have that be a completely separate process of my byte counter data value that's keeping track of how far along I am within that 8-byte burst, where then I'm monitoring the done equals 0. By done, I mean done with my bursts, or done equals 1, meaning I'm done. I've sent all 8 values that are going into my burst here. That logic is also kind of, I would say, separate from this state machine, but it's also required to have, where this is going to be setting some signal that says, hey, increment my counter. I received a valid W ready. I know I've sent 0, now I've sent 1, now I've sent 2, now I've sent 3. There's also, you can either check it directly here, or you could say my counter value equals 8, or my counter value does not equal 8. Or you separately generate a done signal, which is just based on whether the counter value is equal to 8. The important part is not worrying about exactly which logic goes into which process. That's usually not the reason something is working or not working. It's about can you either draw it out or reason about what signals have to be in my system for me to be able to get from one state to the next in my design. And there's no shortcut to kind of designing, coding it, testing it, seeing what's working, what's not working in our design. But when testing it, I think this becomes a little bit trickier than a lot of things that you would normally test, where you can assume everything's really synchronous. A really good, quote-unquote, good test bench would be also testing, all of these receiver side signals, all the ready signals basically would also be testing that. And so you'd want to have a test bench that does things like it waits 20 cycles before it sets AW ready or W ready here, so that you can check that your state machine actually is able to deal with a pause with a wait state that gets inserted into the system. That's a little bit harder to do. And I think in terms of breaking down the tasks you have ahead of you in the lab, starting tomorrow, having someone who really can master that part of the infrastructure will be a very valuable member of the team. Even if they're not writing a single line of code in this part, if they're coming up with really good test cases that allow you to really kind of stress test your designs in simulation, you're going to have to spend much less time in kind of that post-design testing world where you're trying to monitor a single signal at a time to determine what's happening here. So update W data. We have then sent all of our W data. We've sent all 8 bursts. We then are going to have a final set of states for we can call it the receive B response. And here, I do call it receive because the roles are kind of reversed at this point, right? Where now I was this initiator, I was initiating the transaction, I sent the control signals, I sent the data, but now I'm kind of the receiver in terms of that having received something valid from the right response here. Here I am then sending that I am ready for that signal. I'm the one sending this. And I am then waiting for that final valid signal coming from the actual receiver component here, specifying that yes, everything is as intended. All right, well, that'll work, and it's upside down for our purposes. Questions about that example? It's not perfect. It's obviously not the entire VHDL for what we need to do here, but that's the mental model of interfacing with an AXI memory map or the full AXI interface here. There's a couple, and it's complicated, right? There's a whole lot of signals in your design. This diagram doesn't really show the full of it. I guess if you really wanted to see what that looks like in practice, you go back into Vivado, and you see it would be either on the master or the receiver side. It doesn't really matter, but just take a look at it, and then you get to see, for just that interface, there's all those signals that you need to be setting in your design. Yeah, sure, Andrew.
I was just curious, for like the be ready signal, is that just a binary 1 or 0, or does it actually send like some kind of error code? Or
It was defined as the be response, I guess. Ready and valid are 1 bits for that. Trying to drill down even more to get an answer to that question. I don't know. I can definitely look at, okay, we're sending a write request. This generates read request. We'd actually have to get the packet for the write response. Let's see what's included in it. Let's just get the actual answer. Read response packet, read request packet, write response packet, be user, be ID, be response, according to this, is a 2-bit value. So some combination of OK or invalid is sent over a 2-bit signal that we have here. I didn't remember, but I knew the code has to have the right answer for exactly how many bits it needs to be to pack these things in correctly. There's a lot going on with the full AXI interface. I think by and large, you are not having to design and write that state machine yourself in this class. I think you could do it. I mean, if I said you had to do it, I think you would be able to do it. It's not some magic or something like that. By and large, we are interfacing with existing cores that have that logic baked in, and then they provide a somewhat simpler address or interface for you to kind of kick off those AXI transactions and get data back off. What we do have to work with are the so-called lighter interfaces here. So in other classes, if you took like 488, you would have learned about AXI4 Lite. It is a subset of the full AXI interfacing standard. Recognizing, I think, a couple things, that not all IP cores need all this. Not all IP cores need you to transmit 256 bursts of data at a time and have all those different kind of signals associated with it. It's lighter version. It's allow you to have a simpler component to be built that's going to be smaller and just requires a lot less design and implementation effort from your perspective. So the major key feature that it supports is that the burst length is fixed at 1. So in terms of your state machine for interfacing with AXI Lite, it's already a lot simpler just for that reason. You're dealing with a single valid thing getting sent over the bus at any given piece of time. Also, all those other signals that I'm not even really talking about aren't really supported either. So they are there to send just for a single address, a single read or write request at that individual address. That becomes very useful for things like writing to a configuration register on an IP core that you yourself have designed. It's going to be a single 32-bit register. I don't need to send all 256 of anything at a time. I want to either write to a configuration register or read from a status register. AXI Lite is the appropriate interface to do that kind of connection here. What is nice, at least in terms of Xilinx's implementation of AXI for their embedded systems, is I have this big switch here, and you can't really tell kind of by design which cores are going to be connected via the full AXI and which ones are going to be connected via the AXI Lite. It is pin or signal or wire compatible with the fuller AXI. It's just the cores are only going to have to respond to a subset of the total AXI commands. Now, I don't know what would happen if you tried to send an AXI full 256-beat burst to an AXI Lite compatible component. I know it'll happen, it's just not going to work. It's never going to respond to the second beat of the burst. It's just not going to work as intended. So somewhere in the application, in our case it's in the driver, we do have to be aware that if this is going to a configuration register that's actually connected via an AXI Lite interface, we should only be sending one thing at a time. We shouldn't try to send 32 things or 256 things at a time. Because it does often happen that when we're dealing with our IP cores that we want to do multiple things, and this is showing more than what you have currently in MP1. This is just the version of it I just opened up. You are working on, so that's a FIFO, okay. Let me give a better example here. Oh, you have the Vertex Fetch module here, which has got a lot going on. It's oftentimes the case that your IP cores are going to have both. That's not at all unusual. That your IP core is going to need to do two things. It's going to have to request a block of memory from somewhere. That's very common. We're always copying blocks of memory around in our system to get stuff done. And you'll need an AXI full, AXI 4, AXI memory map labeled port associated with that. And it's also very common that you're going to want to configure and or read the status registers off this IP core as well. And for that, we can have an AXI Lite interface. So I'm looking to see, which core individually has both. And looking at subcores, none of these have both. I should be able to find one that has both. Okay, our Vertex shader core has actually a whole bunch of interfaces on it, but it actually does have both. And you do have to get a little fluent with those abbreviations eventually. I don't expect you to know it just off the top of your head, but reading it eventually, ignoring the kind of arbitrary capitalization if nothing else, you should be able to read this and get a hint as to what the interfaces are on this core. Okay, there's an AXI clock and an AXI reset. What does the N mean after AXI reset? Any guess? It's inverted. It's negative edge. When it's 0, we're resetting. You'll get that wrong and you'll lose an hour, but then you'll remember that for the rest of your life, and that's okay. It resets when that signal is 0. You could put an inverter on there. It also kind of shows a little inverter bubble here to kind of indicate that that's what's happening there. There's multiple AXI stream interfaces. We're going to talk about this still today. This is still pretty critical for us. There is an AXI Lite interface. S_AXI Lite. This is a receiver on the AXI Lite interface here. It has some logic in there to expect read or write requests via an AXI Lite interface. It is also an initiator, a master, a sender on the AXI bus, the full AXI bus, and for reasons we will eventually talk to, it has two such interfaces in our system. So this has 1, 2, 3, 4, 5 completely separate bus interfaces on it. Keeping track of what is what based on how those signals are labeled is pretty critical. Because again, even within one of these interfaces, we can look at the light one, there's all those signals we have associated with it. If we were just to draw the full IP core out with every single wire connected to it, it's hundreds of wires associated with just this single IP core here. This is, this is the major leagues here, right? This is big time embedded system design. There's a lot going on. Hopefully these labs are constructed so you're working kind of one chunk at a time and not trying to do the whole design at any one given time. But the IP cores you're designing are going to have that. They're going to have an AXI Lite interface for things like configuration and or status registers. It's going to have stream interfaces, as we'll talk about, because we want to FIFO data around in our system. And it's going to have full-fledged AXI memory-mapped interfaces on them if that IP core needs to read or write from some block of memory somewhere in our system. In this case, this core has 5 such interfaces associated with it. Let me talk briefly about those configuration registers. Some of those you'll be told. Okay, you're creating a viewport core. We can find the viewport core. It's in here somewhere. I swear it's in here somewhere. Well, drilling down on this won't show me anything. It'll just show me the core configuration, which you won't want to change anyway. It's going to have some viewport signals or register values at this memory map. And it's going to say at offset 0, it should be this configuration value. At offset 4, it should be this configuration, etc. But you then have the ability to add as many status and or configuration registers as you want. They just have to hook up to the AXI-Lite interface. So AXI-Lite checks a certain address range, reads or writes to a particular register in that address range, and you will wind up saving time by adding lots of status registers in your design. The one that I personally think is the most valuable, I just hint that you should do this, but let me just tell you should do this, is a status register that just encodes a value for, this is core version number 22. Because I've just made a change to the core and now it's version 22. And I'm going to make another change to the core. You're making a very small tweak. I need to update that register to 23. And then tomorrow, let me update it to 24 and 25. It's an arbitrary, just incrementing number. You're going to lose a lot of time, if you're not careful this semester, debugging something that's actually old code. The tools kind of fight you about this. You have 2 copies of Avado open. You're exporting one core and then importing one core, refreshing user repositories. There's a lot of just steps where it can go wrong. Having an actual configuration register in hardware that specifies this is core ID number 23, because I just tried the first 22 and I'm still making tweaks to it, will save you a lot of time. You at least have that little bit of sanity that in software you can read and say, read this register value, confirm that this is actually core number ID number 23, so that I'm not testing yesterday's logic, I'm testing at least today's logic. And then add whatever debug registers you want. I have a state machine. I keep getting stuck in state number 7, S7. Well, let me connect the actual encoding of that state machine to a register, a separate register, so I can just read from software and just check, oh yeah, I am actually getting stuck in state number 7. Something must not be what I'm expecting to be. Let me also register the actual input values that are coming in. Some assumption I have on paper to VHDL to test is not correct. The more debug information you add, the better off you're going to be in terms of finding that versus where it can start to get a bit of a grind trying to find that information. But that's the value of AXI-Lite. It is the same set of signals effectively. It's kind of pin compatible, but the assumptions you can make it a lot easier to write that state machine, to create that IP core. You're only going to read or write one single value at a time. It's fewer handshakes, fewer other edge cases you have to deal with AXI-Lite. And then finally there's AXI streaming, or AXI-S. Anywhere you see AXI-S in your design, that is an AXI interface corresponding to this. It is, I would argue, only tangentially related to the rest of the AXI interfacing because it's a point-to-point communication protocol. It's not meant to be this kind of send, receive, multiple bursts and things like that. It's meant for that point-to-point communication, and I call it FIFO style because it's very similar to interfacing with a FIFO here. Relatively simple signaling compared to AXI as well as compared to just AXI-Lite. It does not necessarily, I think what I should say here, does not necessarily require a finite state machine to be able to interface with AXI stream. Here are the signals that we have. There's valid and ready. So it's unidirectional. We are sending data from left to right in that diagram. Sender is sending, receiver is receiving. If you need to send data the opposite direction, you need 2 FIFOs. You can't do it with just the one FIFO interface here for AXI stream. We have a valid saying I'm ready to write data. We have a ready signal saying I'm ready to receive data. We have the actual whatever with data field for here is the data that's getting written, and then there's a final single bit for T last indicating that this is the last data packet for now. This can be useful for all sorts of different reasons, but your use of T last is actually kind of system dependent. You get to decide how you want to use that T last signal. Something I didn't bring up when we were talking about this a couple of weeks ago is, one of the challenges we have is when we're sending these streams of data through our system. We're specifying a scene corresponding to vertices with a bunch of attributes associated with it. We oftentimes need some way to encode that we are done. Done with something. I mentioned it briefly. Done with this triangle. Well, maybe every 3 you know you're done with the triangle. Done with this triangle strip. We need to know when we have finished this strip of triangles here and are moving on to the next one. We need to know for different contexts when we are done with a frame. We have sent every pixel we want into our frame buffer and we're not sending any more. We need to encode that information somewhere in our system. And there isn't one kind of guaranteed way to do this. There isn't like one magic way that says, yes, here's how you specify that you are done sending or done processing something. This T last signal is one way we can do it. Other ways we can do it is by having some configuration register in your IP cores where software tells you that it's done. Other times we just have convoluted sets of kind of counting variables where we specify you're going to do this much work, you tell me once you've done this much work and I will monitor when you are done. But you're going to face this as early as MP1 where we have this double buffered frame buffer. Has anyone started on render output yet, that IP core yet? It's straightforward but tricky at the same time. So like getting it 90% working is very straightforward. Getting that last 10% will take you a little bit of time. But we have these 2 buffers, right? The front buffer and the back buffer. The one we draw into and the one we read from. And we have to switch once we're done with the frame. We've written to a frame, now we're ready to read from that same frame. That little mux or that switch we showed a couple weeks ago where one buffer is the front, one buffer is the back, and we just kind of switch them back and forth each time. That's just an address remapping, so there's no actual physical switching happening there. But somebody has to tell that particular IP core it's time to switch. And I don't tell you how to do that. That's one of the things you'll have to solve, kind of last debugging steps for MP1 here. But going back to this interface for AXI streaming, it doesn't necessarily require a finite state machine. You're checking you're setting valid, you're checking ready, and when you get ready high and you have valid high, you're sending data. So that could use a state machine, but it doesn't necessarily require a state machine. If we were to build a core, and let's just talk about it versus just actually doing it here, that was a pass-through type of component. And a lot of your IP cores you're building are going to effectively be pass-through type of components because we have this rendering pipeline, right, where we're receiving some input data and we're also doing some work with it, and then we're generating some output data. So your cores are actually going to look a lot like this, at least at a high-level interface to what they are. It's going to be, you are going to be both a slave on the AXI stream interface because you're receiving data via that FIFO-style interface. You're going to be doing some work with it. And you're also going to be a master on a separate point-to-point interface because you're going to be sending things downstream. You're in the middle of a pipeline, you're both waiting for data, and you're also sending data. We typically will need to have a state machine for doing this because there's no guarantee where the pipeline gets stuck. It's not as straightforward as in CPRE 381. There's a lot of things happening in these stages. There's caches, there's data that's getting sent from the driver. It's never that predictable what's happening in our own pipelines. But ultimately, your cores are going to look like this, plus an AXI Lite interface to configure the cores as well and get some status information back out. You're going to have one interface where you're waiting for data, one interface where you're sending data downstream. Sometimes I use upstream and downstream backwards, but data is coming from upstream, you're processing it, you're sending it downstream. Your logic's going to look something like this at a very high level. So this example is an AXI stream inverter component. The idea being that it takes in an 8-bit value over the AXI stream interface and inverts it before it forwards it on. This can be done in very small amount of VHDL. Because this IP core is an example one that would not require a state machine. You could build it with a state machine. It's just taking data, flipping all the bits in it, that's just all I mean by inverting, and then it's passing it on. We have the 2 interfaces. I just want you to think about this. Your code's going to look kind of like this. Usually, you'll have one process for the upstream interface and a whole separate process for the downstream interface. But for this one, they can really be directly connected to each other for this example. You have one interface that's waiting for data before it does anything, and another interface that's ready to send data when it's available to send data. How could we hook up this core? What kind of logic would we have to draw here? Let's not even do VHDL. Let us do pen engineering here. Not like University of Pennsylvania, like we're gonna use the actual pen here to interface this. How do we wire this component up? Let's start signal by signal. I know I have valid data to send when this signal is high. When is this core ready? When are we ready to send something or to receive data?
Pretty much always.
I would agree with that. This core shouldn't be the cause of any stalls, right? I mean, you can imagine it's buffering and doing some complex math, but this isn't. This is just inverting it, right? In fact, let's, wish I had a touchscreen. Let's actually just wire up the inverter. That is meant to be an inverter. It's not terrible. And literally, M-axis-T data is equal to not S-axis-T data. I don't know if I said that correctly. The output T data is just the inverse of the input T data. It's a pass-through inverter. What else can we wire up here then? I am always ready. I think that's correct. But when am I not ready to pass data on downstream? I'm always ready to invert the data that comes to me, but when am I not ready to pass that data on downstream? When it's not valid, I don't have any valid data to send downstream. I would agree with that. Again, yours may have ultimately a state machine that's waiting several cycles before it, but effectively you are passing that data. I am ready to send, I have valid data to send when I have received valid data to send. Whether you FIFO that signal, whether you store it and then use it later, but I only have valid data when I'm receiving valid data. So that's a wire. You just pass that through. M_axis-st valid is set equal to S_axis-st valid. Doesn't need a state machine. Consequently, when am I ready? Always, yes, but when am I ready to receive data?
When the next block over is ready.
Yes, some arrows would have been helpful here. That arrow goes in that direction. This arrow goes in that direction, right? I'm ready when downstream is ready. And that's not a terrible way to do it, right? Even if I know it's going to take me 10 cycles to process this data, maybe I don't even want to process any data until I know I can actually send that data downstream. That design decision is yours to make. You just have to always be aware of it. You should only receive data when your core is ready to receive data. You should only send data when downstream is ready to receive that data. It is just that pair of signals ultimately that you're responsible for determining what do I do with that information inside my core here. And it can be a little subtle because there's no guarantee that everything is working at the same rate. They're not nicely synchronized with each other. We will eventually get to a point, and even in MP1 you'll get to the point, render output is going to be significantly slower than viewport. Viewport is doing very little work, right? Take an address, change the address is all that viewport is doing. Takes a couple cycles, or do it in one cycle if you can get it to work. Takes a couple cycles, that's it. Render output is also not doing that much work, but ultimately it's writing pixels to the frame buffer. That could take 200 cycles. So this case we're passing through, but in practice you have to be aware that on your viewport, this component I'm connecting to is going to be pretty unreliable. It's going to be very slow relative to what I am. I have to be careful that I don't receive more data than I'm capable of processing. That's what those T-ready signals are for this. And we had FIFOs between each component to kind of try to buffer it out. But still, so if you're off by one, it's usually still okay. But still, you want to make sure you don't read in data until you're ready to do something with it. Finally, how do I know that this is the last data that I'm sending? For the same reason. When I'm told it's the last data, unless I know something better, I tell this component that that was the last data that it had received. Viewport may not know when it's the last data necessarily, but render output definitely needs to know when it's the last bit of data. It needs to know it's time to switch my frame buffers. From what was front is back, what was back is now front. Somebody has to tell frame buffer or render output that. It has no way of kind of inherently knowing that this was the last pixel in a frame. There's no guarantee you send it every single pixel anyway. It's getting whatever data it's getting. Somebody, the driver in this case, has to tell it. By the way, you should be done now. You tell me when you're done processing stuff, that means we're at the end of the frame. let's switch things over. If you're getting very kind of glitchy, flickery, over-tearing kind of images, that's what's happening with your render output component. You're flipping it either too frequently or not frequently at all for those purposes.
So when you say that the render one needs to switch the address, is that just like it's writing an address along with the value and you just need to like switch the value of the frame buffer you're writing to?
Yeah, I think what you'll see is, viewport takes this normalized device coordinates, which we have not talked about, but it takes a value between -1 and 1 for viewport, right? Viewport returns a value that's in window or screen space. It returns an XY thing that looks a lot more like a pixel coordinate, right? Of 128, 256. That's the whole point of the viewport transformation. Render output takes that XY value and does kind of your matrix math to tell you what address in memory does that correspond to. It's stride length times X plus Y, or something effectively that is what it's doing. And then it needs to take that, it needs to add a base address to it, which is the frame buffer base address. That's going to be in one of those configuration registers where you're saying, currently you're writing to address 1 million as our base address, or whatever it winds up being. It's a constant in the driver. We've been writing to that. Oh, I'm done with my frame. Now let's switch what your base address is. So from the render outputs perspective, the logic should still look the same. Take base address value, take XY from my axis stream interface, add them all up together. That's my output data that I'm writing. Is that what you were getting at, or does that kind of answer the question?
I was just asking if you just like switch the base address.
Yeah, you have to wind up just switching the base address. I think the driver has to do that. So software is the only one that would know that I've reached the end of a frame. Hardware doesn't have a way of determining that on its own. Hardware is kind of blind to the fact that we've drawn one frame of a scene and now we're ready to draw the next frame of a scene. Your OpenGL application is the one that first specifies it. I forget what the function call is, but there's one that says GL swap buffers or something like that. I've finished the one scene, one frame, I'm ready to go to the next frame. One way to do that is via GL swap buffers call. Your driver has to capture that. It's not as simple as once it's received that call, instantly changing the frame buffer address, because your driver also has to check, I'm actually done with this scene yet. Yeah, I've sent all the data over, but are we still working on it? Is it still doing the processing required to get that into my frame buffer? Only once it's done and things are stable and nothing's happening in the pipeline, do I then change that base address in the register, and then start the whole thing over again at that point. So that GL swap buffers call should be a blocking one effectively. It should kind of slow down the works, keep processing, then switch things over to the next frame buffer. Okay, let's leave things here for today. You got to make a lot of progress tomorrow in lab, so good luck with that, and ask the TA lots of questions, and I hope you come up with some fun stuff. Thanks.